Hello and welcome to this video on pH of extremely dilute acid solutions explained. We will explain how to calculate the pH of extremely dilute solutions here using this formula pH is equal to minus log of hydrogen ion concentration using a problem given on the next slide. So the problem is a solution of HCl was extremely diluted to a concentration of 10 raised to the power minus 8 molar. The question is what is the pH of this diluted solution? The question here is the pH of this solution, acid solution is really 8? If it is 8, why it is 8 and why it should not be 8? What is the problem and what is the solution? We will discuss those problems and solution in a step-by-step manner in the coming slides. So before addressing the calculations, I would like to go over a few important concepts such as what are extremely dilute solutions, what is the formula for pH measurements, its limitations, pH scale and its definition. So extremely dilute strong acid or base solutions are the solutions which have concentration equal to or less than 10 raised to the power minus 7 molar. So strong here means they are fully ionized at room temperature. So the next important concept is pH measurement using the formula pH is equal to minus logarithm of hydrogen ion concentration. Hydrogen ion exists as hydronium ion under normal conditions, therefore you can also say hydronium ion concentration, and this formula is used specifically for the measurement of pH of strong acid and base. Strong here refers to the fully ionized solutions at room temperature. Using this formula, a pH scale has been developed which will be discussed in the next slide. So using the formula, pH formula, a scale has been developed which is known as pH scale. It ranges from 0 to 14. It has been developed based on the ionic product of water which is 10 raised to the power minus 14. The solutions which have pH close to 7 they are called as neutral, and those which have pH less than 7 up to 0 they are acidic, and those which have pH higher than 7 up to 14 they are called as basic solutions. The corresponding hydrogen ion concentration of each pH unit is given here, and from this you can easily conclude that an increase of a unit of pH corresponds to a tenfold decrease in the hydronium ion concentration in any solution. So this is the pH scale. What are the limitations of the pH formula? pH is equal to minus log of hydrogen ion concentration. It can be used for the measurement of pH of strong acid and base solutions. However, it cannot be used for the measurement of the pH of weak acid and base, and also for buffer solutions. For buffer solution you have to use Henderson-Hasselbalch equation. The question is, can this be used for the measurement of extremely dilute solutions? The answer is yes, it can be used, but you have to introduce slight adjustment and modifications. What is the need of these modifications, why you need to do, and how you will do it? We will just discuss these in a step-by-step manner in the coming slides. So let us calculate the pH of the given acid, extremely dilute acid, using the direct formula pH is equal to minus log of hydrogen ion concentration, and I can assure you that many will do the same way and they will get the wrong answer. So you just plug in the values of the concentration in this equation and you will get the pH equal to 8, which indeed is basic. So has the acid in the question become basic? The answer is no, it is not correct. It is wrong in calculation. Acid can never become a base. So what is the problem? The problem is, if you know that the water's concentration of hydrogen ion in water, pure water, is 10 raised to the power minus 7. So the hydrogen ion concentration in pure water is way more than the hydrogen ion concentration in the problem. Therefore a proper contribution of water must be given to calculate the pH of this solution. Therefore this is a wrong calculation. So next we will calculate the pH by giving proper contribution of water. So let us give the proper contribution of hydrogen ion concentration of water in the calculations. Therefore, the total hydrogen ion concentration in this solution will be hydrogen ion concentration from HCl and that from water. So you transpose the values and you will get this answer 1.1 10 raised to the power minus 7. If you transpose this value in the pH formula, you will get pH equal to 6. pH is equal to 6.96, which is acidic, which makes sense. However, there is a problem. The problem is that this is not pure water, first thing. Second, this has HCl in it, and therefore what will happen, there will be suppression of the autoionization of water, and therefore the hydrogen ion concentration will be less than 10 minus 7 molar. And because we have used 10 minus 7 as molar concentration of water hydrogen ion concentration, therefore we have overrated, and therefore the calculation is wrong here also. So we will how much is the contribution, what is the value of the hydrogen ion concentration of water, we will calculate in the next slide accurately. So let us calculate accurately the contribution of hydrogen ion concentration of water in this problem. So this is the ionization of water. Ionic product of water is equal to ionic the molar concentration of hydrogen ion into molar concentration of hydroxyl ion in water. You transpose the value of these corresponding values and you will get this. Let us assign this as equation 1. Now, so here this is for the pure water, but here in the problem you have HCl, so it is not pure water. So let us assume that hydrogen ion concentration in this equation is not 10 raised to the power minus 7, it is x. Therefore OH will also be x because they are equal to each other. So basically if you transpose this, the value of H plus from water comes out to be 10 raised to the power minus 14 over x. So this is the accurate hydrogen ion concentration of water we have to take into account in our calculation. So now we know the exact value of hydrogen ion concentration in the water. So now let us calculate the total hydrogen ion concentration in this dilute solution. Let us say the hydrogen ion concentration in dilute HCl is x. So x will include the hydrogen ion concentration from HCl together with the hydrogen ion concentration from water. So you plug in these values and you get this equation, right? You multiply both sides by x and you will get this equation here, which is a quadratic equation. Using this equation you can calculate the values of x and then accurately calculate the pH values in the next slide. So let us calculate the value of x from this quadratic equation. The x value will represent the total hydrogen ion concentration of the dilute solution in question. Using this basically equation here, you can use the value, you can calculate the root values of x. They will come as positive and negative integers. Positive integer is considered and negative integer is rejected. So the value of x here represent the total hydrogen ion concentration in the solution, which is equal to 1.051 into 10 raised to the power minus 7. When you plug this value in the formula, you will get pH equal to 6.98. So this is the most accurate, or you can say this is the correct calculation of pH of extremely dilute solution. This has been calculated using or giving the consideration of the water ionization of water and the suppression of ionization of water and also the contribution of water to the calculations. So thank you very much, and I hope your concept regarding the calculation of the pH of extremely dilute solution is clear, and you should be able to solve any problem related to this topic or concept. I would like to request you to share it, to like it, and to subscribe it. Until next time, take care. Bye bye.